Alright, now that we've been introduced to standard position angles, we're ready to define sine, cosine, and tangent for any standard position angle. So let's take a standard position angle starting on the positive x-axis, and I'm just going to, for now, put it in quadrant 1. And I'm going to take a point on the terminal arm, and the coordinates of that are going to be some x and some y. And because my angle is less than 90 degrees in this case, I can think of it as a right triangle, like so. The length from here to here would be the x value of the coordinate. This would be the y value of the coordinate. And this distance here I'm going to call r. Now, we often call r the radius of the circle, and you say, well, where's the circle? What we could do is we could draw a circle through the point, like so. And so, based on our definitions of cosine that we know from the past, which is adjacent over hypotenuse, I can look at this diagram and I can see that adjacent would be the x value divided by the radius. Sine, which is opposite over hypotenuse, would be y over the radius. And tangent is opposite over adjacent, which is y over x. And these are going to be the three definitions of the trig functions you'll want to remember. Because what we can do now is, even though I drew my angle in quadrant 1, I could now move this terminal arm anywhere I wanted. I could move it and still produce sine, cos, and tangent values. Now, just to help you understand this a little better, I'm going to show you an animation. And I'm going to show you an animation that has a circle, but it's going to have a radius of 1. And a radius of 1 circle we call a unit circle. And if you notice over with these formulas, if the radius was 1, the x value here will be equivalent to the cosine of the angle we're talking about. If the radius is 1, the y value will be equal to the sine value of the angle we're talking about. And the y divided by the x will be equivalent to the tangent. So here's my animation. Let me just move it up to, let's say, an angle of 30 degrees. And at 30 degrees, this point right here, its x and y coordinates are shown right here, 0.87 and 0.50. Okay? You'll also notice that the cosine of this standard position angle is 0.87. Its value, the value of cos, is the same as the x coordinate on this circle. Now that's because the circle has a radius of 1. You've got to be careful because often the radius of the circle is not 1. Okay? The sine value is the same as the y coordinate of the point when the radius is 1. And the tangent is 0.5 divided by the x value, 0.87. Now the thing is, these change as I move. And if I move past quadrant 1, you'll see that we can still define sine, cosine, and tangent values. Alright, so here we are at 146 degrees. It's measured from here. This is the standard position angle. You can go to your calculator, type in cosine of 146 degrees, or sine or tan, and you'll get these values. But the meaning of these values comes from this diagram. This point right here, it's got coordinates as shown right there. The cosine is, by the definitions we've established, the x-coordinate of this point, 0.83, negative 0.83, divided by the radius, which in this case is 1. So they're the same. Sine is the y-coordinate divided by 1, so it's 0.55. As you can see, it doesn't matter where we move the angle, we can get a sine, cosine, or tangent value because we're now defining sine, cosine, and tangent based on the coordinates of the point on the circle and the radius of that circle. So let's just go through a little exercise here and you'll see a couple of other connections. Here's my standard position angle. I don't actually know what it is. It's just some theta. But I know that the terminal arm hits the circle at 3 for x and 4 for y. And I could think of there being a circle there. I think it's actually drawn in. I can't quite see it here. And if this distance is 3 and this distance is 4, you could calculate by Pythagoras this distance, which would be 5. And so simply, cosine is x divided by radius, so it's 3 divided by 5. Sine is the y-coordinate divided by the radius, 4 divided by 5. And the tangent is the y divided by the x. which by the way can be thought of as the slope of the terminal arm. Okay, rise over run, change in y over change in x, which is 4 over 3, which in this case is 1.3 repeating. Okay, in the next question, I've got my standard position angle terminating in quadrant 2. So this is my angle. Again, I don't know the exact measure of it, but the point is -3 and 4, which you'll probably realize is a reflection of the terminal arm from quadrant 1 over to quadrant 2. So if I were to figure out what this radius was, well, it would still be the same. It would still be 5. And so my cosine, sine, and tangent values are all going to be based on the same numbers, except that we have a negative for the x. So cosine is -3 over 5, sine is positive 4 over 5, and tangent is positive 4 over -3. Now we're going to reflect the terminal arm from quadrant 2 into quadrant 3. And since we're doing a reflection, the sign of the coordinates just changes. And we're finding the radius based on the same basic numbers, so the radius will be 5. The radius is always going to be positive, by the way. And so I can do my cosine and tan. And let's move it over to quadrant 4. So we're going to reflect the terminal arm from quadrant 3 to quadrant 4, or you can think of reflecting from quadrant 1 to quadrant 4 by crossing the x-axis. The coordinates are now as shown, x and y. The radius is still 5. Now you might wonder why we did this exercise in 4 different quadrants, and probably you were realizing along the way that what I was doing by reflecting the terminal arm across different axes was I was keeping the reference angle, which I'm showing in black here, the same in every standard position angle. The reference angle in all of them, which we don't know specifically, but we know it's the same, because when you do a reflection across the axis, that little piece here will be the same as the piece there. And what happened when we did that is that we noticed that all of our ratios down below were the same as they were in quadrant 1. Our ratios were the same as they were for our reference angle, which we can think of as being in quadrant 1, except for the plus and minus sign. So the value stayed the same, but the plus and minus sign changed depending on which quadrant we were in. So what I hope you noticed through that exercise was a couple of relationships. Firstly, that all 4 standard position angles that I had the same reference angle, and that the standard position angles with the same reference angles had the same trig ratios except for the plus and minus sign. And thirdly, that the sign of the trig ratio depends upon the quadrant in which the terminal arm lies. Here's a question. Find the quadrant in which a standard position angle terminates if you know that the cosine ratio is negative and the sine ratio is positive. So you can think of the cosine ratio as being the x coordinate divided by the radius. The sine is the y coordinate divided by the radius. Okay, let's just sketch this out. Now, in order for cosine to be negative, since we know that the radius is always positive, cosine will be negative whenever the x coordinate is negative. And where on my grid are the x coordinates negative? Well, that would be in quadrants 2 or 3. Remember, it's quadrants 1, 2, 3, and 4. For sine to be positive, since the radius is always positive, y would have to be positive. And where on my diagram are my y coordinates positive? Well, that would be quadrant 1 or quadrant 2. And so for both of these conditions to coexist, my terminal arm would have to be in quadrant 2. Alright, example 2. Write each trig function in terms of its reference angle and then evaluate each expression exactly. So let's draw this out. We have a 225 degree angle, which 90, 180 is a little bit past into quadrant 3. And in fact, how much past? It's 45 degrees. Now the 45 degrees we know is the reference angle. Okay? And we know from what we talked about, the sine of 225 degrees will be the same or opposite of its reference angle. So it'll be the sine of 45 degrees or it'll be the negative sine of 45 degrees. Whether it's positive or negative will be determined by which quadrant we're in. Now we're in quadrant 3, and we know sine by definition is y divided by radius, and we know radius is always positive and y is negative, so we know that my sine ratio should be a negative value. It's going to be the sine of 45 degrees made negative. Well, you say sine of 45 degrees, wait a minute, that's one of those special triangles that we talked about the other day. And what I like to do is I sometimes like to just fit it into this little spot here. Kind of think of this as being 45 degrees. Let me just draw it better here. And my ratios we know are 1, 1, and root 2. Now because I'm down below, this is negative. And so my sine ratio would be the y value negative 1 divided by the radius root 2. Negative 1 over root 2. And just to get the radical off the bottom, to rationalize, I can multiply top and bottom by root 2. And my exact ratio is negative root 2 over 2. Now I imagine some of you are thinking, why can't I use my calculator to get this? Let's just go to the calculator. First of all, in your mode button, be sure that your third line down is set to degree mode, because we're measuring our angles in degrees. And so let's type in here sine of 225. We're expecting to get a negative value because we're in quadrant 3. Sure enough, we do. The issue is that this is not an exact value because this is an irrational number. It goes on forever without stopping. So there's no way to write it down exactly. And so we have to go through the thinking and the analysis that we just did here to come up with this value. Now this value that's circled should be the same as the decimal I see up above. Let's just type it in to make sure. And indeed it is. Final question. We have a standard position angle that has a terminal arm passing through the point 4, negative 6. Here's the terminal arm. So the angle is something like that. I don't know the measure of the angle. And if you'll notice by the question, we're not even asked to find the measure of the angle. We're asked to find the value of the three trig ratios. So we're asked to find the cosine of the angle, the sine of the angle, and the tan of the angle. And you say, you mean I can find that without knowing what the actual angle is? You can, because we know the definitions of sine, cos, and tan are determined by the x and y coordinates of the point on the terminal arm and the radius. Now, we're able to do the last of these calculations because we know that the x and y coordinates are shown. So for tangent, it's negative 6 over 4, which is negative 3 over 2. The tangent ratio of this angle, whose measure I don't know yet, and you might have some ideas on how to get that, but we're going to talk about that in the next video. The tangent ratio is negative 3 over 2. Now for sine and cos, we need the radius. And remember that you can think of a circle going through the point on the terminal arm. So you can think of this as being the radius, r. And if you want to narrow in on the reference angle, you could think of this as being 4 units over, this is the way I like to do it, 4 units over, negative 6 units down, and then there's my radius. And so I could do Pythagoras to calculate that. So therefore the radius is the square root of 52. And let's just reduce this radical. That's root 4 times root 13, which is 2 root 13 is the radius. So going back up above, the cosine ratio is now the x-coordinate, 4, divided by the radius. And the 4 divided by 2 can be reduced to 2 over root 13. And to get the radical off the bottom, we can multiply top and bottom by root 13. And so we get a ratio of 2 times the square root of 13 divided by 13. The sine ratio, just to squeeze it in, would be negative 6 over 2 root 13, which would equal negative 3 over root 13, which would equal negative 3 root 13 over 13.